Ever thought about the reason behind the fizz sound while opening a soda bottle? Yes, there is dissolved gas inside the liquid. It escapes from the bottle, which results in a fizz sound. This means the gas is dissolved in a liquid and it forms solutions. In this video, we discuss the theoretical aspects of dissolution of gas in a liquid. Observe this graph. Observe it very carefully. You can see this graph gives a solubility of oxygen and carbon dioxide in water. Here you can see carbon dioxide is more soluble in water than oxygen. In fact, dissolution of gas in a liquid is at dynamic equilibrium. That is, the rate at which gaseous particles enter and leave the solution phase is the same. When you increase the pressure, say P2, such that P2 is greater than P1, then what happens is that a larger amount of gas, it will dissolve in the solvent. This quantitative relationship between pressure and solubility of a gas in a solvent was first proposed by William Henry, and that is now known as Henry's law. This law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. During the same period, Dalton, he independently concluded that solubility of a gas in a liquid solution is a function of partial pressure of the gas. So, if you express solubility in terms of mole fraction, then Henry's law, it could be stated as mole fraction of a gas in the solution is proportional to the partial pressure of the gas over the solution. However, most commonly, Henry's law is stated as follows. The partial pressure of a gas in vapor phase is proportional to the mole fraction of a gas in the solution. This can be mathematically represented as P is directly proportional to X, or you can write P equals Kh into X, where Kh is called the Henry's law constant. Now we can see the graphical representation of the equation. If we plot the mole fraction of a gas in a solution versus its partial pressure, then you will get a straight line which passes through the origin. The slope of this line gives the Henry's constant Kh. This clearly implies that as partial pressure increases, the mole fraction also increases. Here you can see the Henry's constant for certain gases. From the table, you can infer that Kh increases with decrease in temperature. Consequently, what happens to solubility? Solubility, it decreases with rise in temperature. Alternatively, if dissolution is considered similar to condensation, then dissolution is an exothermic process. That is, it is in dynamic equilibrium. So, it follows that solubility should decrease with increasing temperature. This will be according to Le Chatelier's principle. Next, we look into the applications of Henry's law. Do you know why during the preparation of carbonated drinks, the bottle is sealed under high pressure? This is to increase the solubility of carbon dioxide gas in water. You may also find the application of Henry's law in scuba diving. The amount of dissolved gas in blood of a scuba diver at deep sea is very high. This is because the pressure is high in deep sea. If the diver returns too rapidly to the surface, what happens is that these gases, it will form bubbles in blood because it is less soluble due to the decreased pressure at the surface. These bubbles stop the flow of blood to organs. This results in a condition which is called bends, and this condition is lethal in nature. To avoid bends, scuba divers, they carry artificial breathing mixtures which usually contain helium. As helium is 5 times less soluble in blood than nitrogen, there would be less dissolved gases such that it will not form bubbles. Yet another application of Henry's law is observed during mountaineering. At high altitude, the atmospheric pressure is lower than at the ground level. So, mountaineers, they will suffer from anoxia. It is a condition in which, due to low oxygen in blood, the climbers become weak and they cannot think clearly. Hence, they carry oxygen cylinders at very high altitude. With this, I hope you are clear about Henry's law and its applications. Now, can you tell me the reason why aquatic species, they are more comfortable in cold water rather than in warm water? Think about it. Now, let's summarize what we have learned today.
Manorama Horizon. Learning made simple.